Alrighty, so sum and difference amplifiers are a special type of op-amp circuit which allow you to take multiple inputs and output any linear combination of those inputs. So a linear combination is just a scalar multiplier. Each of these inputs has a scalar multiplier. This can be positive or negative, and then they're all being summed up to get your output. So this is a sum and difference amplifier right here. You see we have some that are going into our non-inverting input or non-inverting input for the op-amp, and these two over here are going into our inverting input. So just intuitively we can tell that the gain constants for V1 and V2, this A and B, is going to be positive. They're going to be added to the total. And the gain constants for V3 and V4 are going to be negative since they're on the other side. Alrighty, so we need to find the function for V out, which means we need to find each of these individual gain constants, the weights on each of our inputs. So to do that, we're just going to go ahead and start with some node voltage analysis, labeling our circuit. We know this is Vin and this is Vp. Because we're using the ideal model for the op-amp, we know these two are equal. And those are the only two nodes that we have to worry about, it looks like, in this situation. So let's go ahead and write out some node voltage equations. For Vp, we have 1, 2, 3, 4 currents, but we know the current going in to the op-amp is 0. So we're just going to deal with these 3 right here. So the first one, we'll do Vp minus V1 divide by 28 kiloohms, and then add Vp minus V2 divide by 21 kiloohms. Then we're going to do Vp minus 0, since we're going to ground, divide by 12 kiloohms. And all this is equal to 0. Alrighty, and now we can write out our node voltage equation for Vin up here. So same story here. No current going into our op-amp, so the only ones we have to worry about are to the output and to our two inputs. So let's go ahead and write that. First, the one to the output, we're going from Vin to Vout over a 40K resistor. Then we're going from Vin to V3 over an 8K resistor. And then finally to V4 over a 5K resistor. All that's equal to 0. So we have our 1, our 2, 3 equations, and we have lots of variables here, but the only ones that we need to solve for are Vout, Vin, and Vp. Since those are, we want to get rid of Vn and Vp, since we do not want those in our final equation. And we want to solve for Vout, since that's what our final equation is in terms of. So all these V1s, V2s, V3s, those are also variables, but we can maintain them because our final equation will also have those variables. So this is an adequate amount of equations right here. So the first thing I'm going to want to do is get rid of all these fractions just to make things easier. So I'm going to multiply all this by the least common multiple of 21, 28, and 12, which can be found if you are like me and don't like doing number things in your head using your calculator. So we're going to multiply by 84K. And 84 divided by 28 gets us 3 VP minus V1. 84 divided by 21 gets us 4 VP minus V2. And 84 divided by 12, that's just 7 VP. So all that is still equal to 0. We can do the same thing down here. Least common multiple of these is a little easier to find. 8 times 5 is 40. 40 over there, so we're just going to multiply it all by 40K. We get V in minus V out plus 5 times V in minus V3 plus 8 V in minus V4, all equal to 0. So now we want to try and solve for Vn and Vp in each of these equations so we can set them equal to each other in our final equation. So let's go ahead and do that for the first one here. We're going to have 3 VP plus 4, 7, plus 7, 14 VP, and then minus 3 V1, and minus 4 V2 equals to 0. So 14 VP equals to 3 V1 plus 4 V2. And we can divide over the 14. Now let's try on this one. So we have Vn 5, so Vn plus 1, 6, plus 8 gets us 14 Vn minus V out minus 5 V3 minus 8 V4 equals to 0. So 14 Vn equal to V out plus 5 V3 plus 8 V4. It looks like we don't have to divide by the 14 because we have 14 VP over here and 14 Vn over here. So we can go ahead and just set these equal to each other. So the first one, 3 V1 plus 4 V2 is equal to our second equation over here, V out plus 5 V3 plus 8 V4. Alrighty, so we now have an expression that contains V out and multiples of V1, V2, V3, V4. So now we just need to get V out on the left side. So we get 3 V1 plus 4 V2 minus 5 V3 minus 8 V4. And this is our final answer as V out as a linear combination of our op amp inputs.